Hi class, welcome back to Multivariable Calculus. In this lecture, we are going to be returning to working with double integrals, but this time we are going to evaluate double integrals using polar coordinates. So let's just get right into it. Polar coordinates are related to Cartesian coordinates as follows. So r squared is equal to x squared plus y squared. X is equal to r times cosine theta, and y is equal to r times sine theta. And of course, in this case, theta is in reference to the angles you are from the x-axis, right? Because that would mean that it's the distance r, so some radius, times the cosine of that angle from the x-axis. So cosine will give you the x, and sine will give you the y coordinate. So looking at the polar rectangle, it's going to just be, let's look at it on y versus x, for example. And what we're going to do is we're going to set up our polar rectangle. And we are going to call this shaded region R. And so let's work out what these limits are. So let us start with this lower piece right here, this lower limit. So I'm just going to project this back down. And in this case, this is going to represent an angle of theta is equal to alpha. So theta equals alpha. And then this will represent an angle of theta equals beta. So out here we'll have theta equals beta. And then moving this way, we're going to have a lower limit for a radius. So radius is equal to a. And then we're going to have an outer extent of a radius where r is equal to b. So we can just think of a circle, right, where you have some radius r. And of course, if you had a lower limit set on r and an upper bound set on r, what you'd be looking at would be more of like a donut. And in this case, because you're not going around and sweeping out the full circle, you're just going to have a little sliver of that donut or a wedge. And this is what is called the polar rectangle. So our region R is going to be a function of our radius bounds and our bounds for theta. Okay, so now we're working in terms of r and theta instead of the Cartesian coordinates x and y. So our region R is a function of r and theta such that a is less than or equal to r is less than or equal to b. Okay, so those are our limits on the radii. A is the inner and b is the outer. And alpha is less than or equal to theta is less than or equal to beta. Okay, and those are the limits on the angles swept out. So there's alpha and there's the extent of beta. And so to change to polar coordinates, if f is a continuous function on the polar rectangle R, so if f is a continuous function on polar rectangle, I promise it says rectangle, R, what we have is we have the double integral over our region R, where you have some function of x and y, dA, and remember dA is dx dy, can be converted to polar coordinates as follows. So we're going to go from alpha to beta for theta, and a to b for r, and our function then needs to be converted from x and y to r and our trig functions. So x is defined equal to r cosine theta. So f is going to be a function of r cosine theta, and y is r sine theta. And dA becomes r dr d theta for the conversion. Okay, so you have an extra r in there. So it's r dr d theta because an area, right, is going to be some length squared. And so these angles are really just, they're in radians, they're dimensionless, right? And so we have, the dimensions have to work out. And so you have an extra r in there. Okay, so let's go and try out an exercise together. And we're going to evaluate the following, where R is the region in the upper half plane bounded by the circles x squared plus y squared is equal to 1, and x squared plus y squared is equal to 4. So let's first just sketch out our region. So we have y, and we have x. And so our upper bound was set by the equation x squared plus y squared is equal to 4, right? So that would mean that we have x going from -2 to 2, and y is just going to be up to 2 because we're looking at the upper half plane. And so then our lower bound is going to be given by x squared plus y squared is equal to 1. So that'd be a radius of 1. So it goes from -1 to 1 for our x and up to 1 for our y. And I know that's not anywhere close to perfect. Okay, and so there's our region. Shade it in a little. Okay, so this is the region we're looking at. And the lower bound is x squared plus y squared is equal to 1. Okay, so some things to take note on. So it's clear that our radius in this case is going to go between 1 and 2. And the other piece, right, our radius is from 1 to 2. The other piece to think about is that we have to think about our theta. And so in terms of pi, here we'll be going from 0, 1/4 of the way around is pi over 2, and 1/2 the way around is pi. And so if we were going all the way around, we'd be going from 0 to 2 pi, but we're not. We're only going to be looking at the upper half plane, so we're looking at half a circle. So for theta, we're sweeping out from 0 to pi. So let's rewrite our integral in polar coordinates. We have the double integral over our region for 3x plus 4y squared dA. So our bound for theta, we decided it was from 0 to pi. Our bound for r is from 1 to 2. So now what we have to do is for x, we have to plug in r cosine theta. So this is going to be 3 times r cosine theta plus, and then for y, we have to plug in r sine theta, and so this is y squared. So we have 4 r squared sine squared theta, and then we still have to multiply by r dr d theta. Okay, so now let's just start evaluating. So let's first just distribute this r throughout. And so we're going from 0 to pi, and from 1 to 2 for our r, and we're going to have 3r squared cosine theta plus 4r cubed sine squared theta dr d theta. Okay, so starting with the inner integral, keep the 0 to pi on the outside, and we are gonna have to integrate in terms of r. So we have 3r squared cosine theta is going to become 3r cubed over 3 cosine theta, which is just going to be r cubed cosine theta. And then we're going to have 4r cubed sine squared theta, which is just going to become 4r to the 4th over 4 sine squared theta. So it's going to be plus r to the 4th sine squared theta. And we're going to evaluate this from 1 to 2 for r. And we're still left with a d theta. So this is going to become the integral from 0 to pi of r cubed cosine theta, and 3 cubed is 8, plus 2 to the 4th is 16 sine squared theta, and then we're going to have to subtract off, plugging in 1 for r, so 1 cubed is 1 cosine theta, plus r 1 to the 4th is 1, so sine squared theta, and we still have our d theta. Okay, so I'm going to keep going on another sheet. So this is still 26.1. Okay, so we have integral from 0 to pi, and so it's going to be 8 cosine theta minus cosine theta, which is going to be 7 cosine theta plus 16 sine squared theta minus sine squared theta, which is going to be 15 sine squared theta d theta. All right, So now let's integrate in terms of theta. And we're going to end up with, well, let's see, we have a half angle identity we can use here. So let's rewrite this one more time. If we go from 0 to pi, we have 7 cosine theta. And this is going to be, we're going to use an identity here where sine squared theta is equal to 1/2 times 1 minus cosine 2 theta. And I have, on Moodle, there's a trig cheat sheet on there with these different trig identities. So be familiar with those because you're going to have to use them sometimes to simplify your integration, your integrals. So otherwise, this would be it would be really hard to evaluate in this current form. So we're going to use this half angle identity, and it's going to be 15 over 2 times 1 minus cosine 2 theta, and we still have our d theta. All right, so let's integrate. So 7 cosine theta becomes 7 sine theta, and 15 over 2 times 1 d theta becomes 15 theta over 2. And then cosine, or well, minus cosine 2 theta becomes, and we still have our 15 over 2, so that's going to be 15 over 4 sine 2 theta. And we are going to evaluate from 0 to pi. And so this is going to become 0 plus 15 pi over 2 minus 0. So we get 15 pi over 2. Right, and you can test this out, because what you're dealing with is, remember that equation for area of a circle is pi r squared, and you have a radius of 2, so it's going to be 4 pi minus pi, right? So you're going to have the area there, and then you're going to have half a circle. All right, and this is, but you're integrating to get the volume under this region. So 15 pi over 2. So now we're going to find the area enclosed by one loop of the four-leafed rows r equals cosine 2 theta. So I'm going to draw out the four-leafed rows for you. All right, so it's basically just kind of looks like a clover. All right, pretend each one of those petals are equivalent to one another. And we just want to know the area enclosed by one loop. So if we looked at this, we're going to have one loop. Let's set the lower bound to theta is equal to minus pi over 4. And the upper bound is going to be equal to theta is pi over 4. Okay, so we're going to go from minus pi over 4 to pi over 4. And go ahead and pause this and try it on your own if you'd like. And then hit play when you're ready to see the solution. So let's see. We're going to go from minus pi over 4 to pi over 4. And we're going to go from 0 to cosine 2 theta. So quick side note here. If I seem a little distracted, it's because I live in a 1-bedroom apartment that's 2 floors, but it has no doors. And my husband is teaching a class downstairs at the same time as I'm teaching a class upstairs. So if I start to like drift off or say something funny, I apologize. I'm going to try to focus as best I can, and you're probably hearing an English lecture or philosophy or something going on in the background. So that is what that rumbling is. Anyway, let's keep going. And so we have r dr d theta. Okay, so that's dA in polar coordinates. It's r dr d theta. So we're looking for the area enclosed by one loop of the 4 leaved rows. And so we're going from 0 to r is equal to cosine 2 theta. And we're going from minus pi over 4 to pi over 4. So now it should be pretty straightforward that we have it set up. So we have minus pi over 4 to pi over 4. And so r dr is going to become r squared over 2. We're going to evaluate this from 0 to cosine 2 theta. And we still have our d theta. Okay. And so we can pull out a half, since that's a constant. And we're going to go from minus pi over 4 to pi over 4. Okay, and so we plug in cosine 2 theta for our r squared, and we end up with cosine squared 2 theta. And we still have our d theta. And so we can use that identity again that we used last time. And so we have 1 over 4 times the integral from minus pi over 4 to pi over 4 of 1 plus cosine 4 theta d theta. And this is the identity, this is slightly different. This is the identity that cosine squared 2 theta is going to be equal to 1/2 times 1 plus cosine 4 theta. Or another way to think about it is cosine squared theta is equal to 1/2 times 1 plus cosine 2 theta, right? I just doubled it here. So you'll also see that on the trig sheet I have posted. And so let's integrate. This is going to be equal to 1/4. Okay, and then d theta, 1 d theta just is theta. And then cosine 4 theta becomes sine 4 theta. And we're going to evaluate from minus pi over 4 to pi over 4. So what we end up with is we get 1/4 times pi over 4 plus, or minus a minus pi over 4, which is plus pi over 4, which gives us pi over 8. So you should get pi over 8. Okay. Well, that is it for today, and I'll see you next time when we practice evaluating triple integrals and converting them to cylindrical and spherical coordinates. So see you next time.